Hey, hi guys, Phil here with notes on linear algebra. One of you has encouraged me to make some notes, so let's see how many of you make use of this video. For those of you who are not taking this course, this is one taken by first year undergrads majoring in management, finance, accounting, and other social sciences. They've got varying backgrounds of maths. Some have done quite a lot, some have done quite a little at school. But they're hardworking guys and girls and pretty nice bunch of people to teach, may I say. But yeah, it's not like they're doing maths because they love it or they're really great at it, alright? So that's the background. I'm just going to say basically what you need to know, so it's not like lecture notes, it's just like, revision notes is what revision is. So here are the bullet points, and I'm going to go through them one by one. First, solving system of linear equations. Let me start by reminding you of what we did like in the first class. We had a model of supply and demand. We wanted to find the equilibrium level of quantity and price. That's like two equations in two unknowns, and you all know how to solve that. We're finding a point of intersection, which is where they cross, and that gives us the price and quantity. Where we need linear algebra is when we've got loads and loads of equations, big systems, loads and loads of equations, loads of unknowns. Then the method that you use to solve two equations, two unknowns, will be just too unwieldy. Okay, so we learn some neat techniques to solve big systems. Right, I'm doing this off the cuff, so I hope I don't make any errors. But if I do, just let me know. It is kind of turning midday, so I'm just about awake. All right. The most important equation in linear algebra for us, right, is ax equals b. That's my number one equation. That's what you go to bed thinking about, like the day before the exam. Ax equals b. This is a matrix times a vector equals a vector of stuff. This, what we notice is that big caps is reserved for matrices, little one for vectors. All right. Now this a here, it's got say m rows, number of rows, and n number of columns. So we write something m by n. It's up to you whether you use that notation. You might use some different symbols, but I'm just saying that. So m stands for number of rows by n number of columns. So it's that way round. Okay. So this says m number of rows, n number of columns, whatever m and n are. They're just numbers. So m will denote the number of equations in my system. N will denote the number of unknown things, variables I have to solve. Okay, and B is a vector of numbers. Just to remind you, we'll write something like this. If this is m by n, put in brackets, this guy here must start off with an n. Okay, it's a vector, so it's n by 1. This is also n by 1. How do I know? Well, because remember what I said, when you're multiplying a matrix with a matrix or a matrix with a vector or whatever, it will only work if the two inner numbers match. Here it's n, whatever that is. Okay, they match so that you are able to multiply them, because in general, if I just do a matrix A times a matrix B, it doesn't mean that you can actually multiply them, not like with usual numbers where you can. The answer will have m number of rows and that many number of columns, so it's m by 1 here. So this should be m by 1, thank you. Alright, m by 1. Quick example of something we can write like that. Let's look at two equations, two unknowns. 3x plus y equals 5. X plus y equal 3. We've got two equations, so my m is 2. How many unknowns? X and y are the stuff to solve for. Two unknowns. Let's write it in terms of ax equal b. At this point, I want to just say that I'm using the notation that you're used to seeing, but I have to be careful here. This x, right, is the vector of x's, and the variables is curly x, curly y, so these x's are not the same thing. Alright? So, how do you do it? Well, I know I must have two rows, two columns, because it's two equations and two unknowns, so I make enough space for that. We write down the coefficients of each of these guys. So it's 1, so it's 3, that's that one, and 1, 1 and 1, 1 and 1. Alright, and then in here it's little x, curly y. Here it's 5 and 3. How do I know I got that right? Here's another way of looking at it, guys. 3, 1, 1, 1. Imagine this guy, this vector here, like, suppose it's some kind of like a train carriage or a snake. Let's just kind of, if you imagine I can maneuver it, just pull it around there, then and let's do it in a different color. That's x and y. All right. I just do it in a different color because I don't. It's just for me to understand what I'm doing, and I just write that like that. So if I'm multiplying out, it's just like 3 times x plus 1 times y. 1 times y. Okay, and the second equation would be 1 times x plus 1 times y. Right, so that is the same as writing this. Right, that's going to help for the next thing that we're going to look at. Row view, column view of AX equals B. Right, we didn't use the word row view and column view in the course, but what I've just done there is what they call the row view. So it's each equation is written out in full equals a number on the other side. That's what we're used to doing. That's what you're most comfortable with. The thing that you don't know about is the column view. So if we look at this is where it helps, this kind of thing that I'm doing. Column view. Typically a question says, write down, express the vector b, which is on the right side of AX equals b, in terms of the columns of the matrix A. What it means basically is this. Let's write back what we started here. It says, all we do is this. 3 and 1, that's the first column of A, just write it down, times by the variable x. And then you go plus, that's the second column of A, just write that down, and times the thing above it, y. Okay, and that's equal to 5, 3. That's the equivalent of way of writing this. Alright, this guy is what I call column view, but it's in the question as I said, they'll typically say like express the vector 5, 3 in terms of the columns of A. That's the first column of A, that's the second column of A. Now there are nice pictures for this, what they call the row view, and this, what they call the column view. And some of you might have seen it in school, but we didn't show. I don't think you did it in lecture, so it's nice to see, but it's revision, so I'm not going to do it because at this stage I think you appreciate that. I'm just telling you what you need to know. Alright, now 3 kind of special matrices. The identity matrix denoted by I. Okay, if I do now the vector, it's this identity matrix is a bit like the number 1 in normal numbers, so times by any other matrix gives that matrix. And what we do is indent it by some number that tells us how many rows and how many columns it's got. So if I do 2, it's 1 where it's got 1 along the diagonals and 0 everywhere else. Okay, that's called the identity matrix. If it's I3, that's going to be 1, 2, it's got 3 rows, 3 columns, 0 everywhere else. What's to come later, I could write this as just 1, 1, 1, and a great big 0 to mean 0 all above it, great big 0 to mean 0 everything means 0 below it. Alright, so that's like all zeros. This is like all zeros. And the identity matrix, a property of that, say I pick a matrix A, right, where they've got this, where we can actually the same dimensions, and it's the same as A times I, same as A. It's like the number 1 times another number 3 is equal to 3 times another 1 equals 3. Alright, similar kind of thing. That's what the identity matrix is. Next thing, is the square matrix. Alright, a square matrix just means it's a matrix with the same number of rows and columns. So say m number of rows by m number of columns. That is a square matrix. Finally, the inverse of matrix, say A, of a square matrix A. So given a square matrix A, the inverse of it, denoted by that, satisfies the following, is the inverse of A. And it is also M by M, right? They match. So it's A inverse times the matrix times A, the other way around is equal to the identity. Okay, so it's just like 1/3 times 3 equals 3 times 1/3 equals 1, isn't it? Alright, so you could think about something like that. It's very important to note it's square matrix. So if it's not square, for example, if it's 3 by 2, then the inverse as we know it won't exist. So multiple choice question. Can you use the usual methods to find a inverse of a 2 by 3 matrix? The answer is no, because it isn't square. Okay, at this stage I feel like I've already talked a lot. Solving, next bullet point, solving AX equals B by augmented matrix form. So, what we want is augmented matrix. That means write A, B. Okay, this is now augmented matrix. And then what do? We use the row operations. Okay, row ops, which you memorize what they are. We'll talk about in a minute. And when you do that, one of three things can happen. You can end up with no solutions, unique solution, or one solution, infinitely many solutions for the problem AX equals B, i.e. this guy we're looking for. That satisfies all these equations. So when we do the row operations and you get to the stage, no operations will look a bit like this. You're going to get a row of zeros somewhere on this side, but this side, this is not 0. Okay, it could be negative or a positive number. If you reach something like that, that means there's no solution for the system. It doesn't matter what's up there, okay? It doesn't matter what's up there. Unique solution means that I can end up with ones all along, leading ones all along the diagonal. Above it we don't care what we have, and below it we've got to have all zeros, great big fat 0, and along here then I don't care what I have there as well, numbers or zeros and different numbers that are not zeros. That's a case of unique solution. Infinitely many solutions, alright, that's where we can get at least one entire row of zeros. Okay, here we have one entire row of zeros. It's different to this because where no solutions, because zeros is only on like this left hand side and not on the right hand side, whereas this 60 zeros is right the way through. So what does it mean anyway? Graphically, let's think about this. You can think about it like this. It's in terms of two equations, two unknowns. If there are no solutions, right? My small curly y, curly x. It's like these lines do not intersect at all. So that's like, say, the line of my first equation, line of my second equation. No point of intersection. Remember the first picture I showed you about the equilibrium? There was at one point of intersection. Here, they're like parallel, no points of intersection. Unique solution, well, that's an example of that was supply and demand. So we had one point of intersection. That's unique, and it's given by that. Infinitely many. Say my first equation is a line like that, because I've got two equations, two unknowns. The second one will be exactly on top of it, because look, you can see anywhere it crosses is a solution. Well, that's got infinitely many points of intersection. So when you're solving this thing, that's kind of, you can keep in the back of your mind, that's what it means by solution. That's what you're trying to see, which of these pictures it is. Of course, for higher systems where you've got more equations, more unknowns, it's not. But for the purpose of just thinking about simplistically what you're doing, this is what you're doing, right? If you're kind of losing track of what on earth you're doing. How is this related to the inverse? It's good if you get all this on one bit of paper, because then you can see exactly how it all relates. The inverse is like x. If there's a unique solution, we can solve it as x a inverse. Let's just write ax equals b, right? That's what we're trying to solve. That's what we're trying to solve. X is equal to a inverse b, and a inverse exists. In the case where no solutions, the inverse of a does not exist. This is supposing, it's supposed to say that we're starting off a as, well, a is a square matrix, by the way. Yeah, a is a square matrix. Where there's infinitely many solutions, a inverse does not exist either. In other words, when you're trying to find a inverse, if it exists, it means that this problem, ax equals b, has one solution. If it doesn't, it's either no solutions or infinitely many solutions. And that leads us to the question of how do I find a inverse? Right, a inverse, I do a similar thing to the augmented matrix. So I write, to find a inverse, I write a and identity. Okay, where this is a square matrix, so it says m by m, and this must be of the same, what we call dimensions. It's got to have the same number of rows and columns, so it's m by m as well, right? And we can do row operations, and one of two things can happen. We can get to change the left hand side from a to I, and then the right hand side will be the inverse, or we'll get to the stage where we've got one row of zeros and then we stop. So that's the inverse exists, and it's given by that right hand side right there. Inverse not exist. So we also use the row operations that we used for the above. I didn't say anything about, let's recap what these row operations are. So we can, what can we do? We can multiply one row by a non-zero number. Yeah. What else can we do? Can interchange rows, because that's just like rewriting the system. What does it matter that you write the first equation second, the second equation first? You know, you're just kind of juggling things about. It doesn't matter. And one other thing you can do is you can add one row to another. Okay, so yeah, when it comes to like solving for this augmented matrix, it's kind of like mamma mia. It seems like a big task, isn't it? Yeah, but although for the exam you won't have such a big system to solve. Let me now give you 3 examples, one of each: no solution, one solution, infinite many solutions of ax equals to b. Example 1. Alright, so let's say we just so you can see how the row operations work. Let's say my A matrix is this guy, and no solutions, so 3 and 5, let's say. Okay, I want to do row operations. The idea is that I have first row, first column, that's got to be a 1. I've got to end up with a situation where the second row, second column must end up with a number, or you know, by standard we want to set that to 1 as well. So in other words, 1 all along the diagonals, zeros below it. That's what I'm after. And upstairs, we don't care whether it's all zeros or not. Okay, so what do we do thinking about Mia? Well, when doing linear algebra, as soon as you get one thing wrong, the whole thing is wrong, so take your time. So what I want to do, that's already a 1, so I'm going to just write that down. This guy here, I'm going to have to do some operations. So for my own notes, I'm just going to write here, I'm going to have to times this guy here by -2 and add it to that to turn that bottom one to 0. So I'm going to add to row 2 -2 times row 1. That's for my own notes. Right? It's good to do that just because when you're doing these things it's tedious, but you can it's easy to make a slight slip. So -2 times 2 is -2, 2 times, yeah. Add to 2 is 0. Okay. -2 times 2 is -4. Add to 4, that's 0. -2 times 3 is -6. Add to 5, that's -1, isn't it? Okay. So I can see the case is no solutions because I have zeros on this side but a number that is not 0 on the right hand side. So implies no solutions. That's example 1. Example 2. What we're going to do, say there's going to be one solution for this one. We're going to do 1, 1, and let's say 3, 4 down here, and let's say this one is going to be 2 and 7. Row operations. Okay, so it's same idea. That's already 1, so I am going to keep that row as it is, so I write that down. Right, and then the second row, I want to turn that 3 into 0, so to do that, I multiply this top one by -3 and add it to the second, don't I? So I'll go plus -3 times row 1 to the second one. Okay, so -3 times 1 is -3, add it to the second one, that's going to be nothing, 0. I want the same color, 0. -3 times 1 is -3, add to 4, that's +1, yeah? And -3 times 2 is -6, 7, it's 1. I can stop here because I got zeros below, 1 along diagonals, and there's 1 there. This means that there is one unique solution. But I can take it further. To kind of facilitate the backwards elimination, the final step to find my variables, I can eliminate that. How? Because can you see if I multiply this second row by -1 and add it to the first row, now that will get rid of that. So let's just do that. I don't have to, but I'm saying that because often it facilitates the rest of the calculation, what I call the back substitution. Alright, now in terms of jargon, terminology, you don't have to know this, I guess. This is, but some people do. This is called the echelon form. Am I going to be able to spell it right? Echelon form. This guy here, because it's basically, if you look at it, it's what called upper. It's like an upper triangular. All right, it's like I've just drawn a triangle there. Whereas this guy here is called the reduced echelon form. Some people kind of want to know the distinction between the two because they hear it talked about. So distinction is that you can see the reduced echelon form is like we reduce it further, we turn everything upstairs is also 0. Okay, final example, infinitely many solutions. Let's say we've got 1, 1, 1, and then 2, 2, 2. You can see if I multiply the top row, I'm going to turn that 2 into 0, right, because that's below the 1. So I multiply, must mean I multiply the top row by -2 and add it to second row. Since you can see that the 2 is exactly just twice everything of the first, it's just 0, zeros everywhere, isn't it? Yeah, and so there's a whole row of zeros, so that means there's infinitely many solutions. And if I just kind of use a method I showed you before, this is like my column of x, that's column of y, in A, x equals b, A being the great big matrix. This strong x is equal to curly x, curly y equals b, alright? So that's this guy here, is over here. So that is like my leading 1, that's the x, but the y has no leading 1, in the second row, second column, that should be a 1 there, but there isn't. So what do we say? We set it to what they call a free parameter, and that doesn't mean number 3. So this is like where you say let y equal some letter, entirely up to you, let's say t, where t is any number on the real line. Okay, so t is a free parameter in that sense, because it can take on any number you like on the real line. Alright, good. So we've done, how many things have we done? The 6 things there. We've done 5. Find inverse. Yeah. So all we're left with is the input-output model. Okay, input-output model. We've got a vector, big X, equals AX plus D is what we want to remember. And the other one we want to remember is from this first equation we can derive this I and that minus A minus D. These things, we better write down what they are. X is a vector, and it's a vector of what I call the production schedule. So the stuff that we need, production stuff we're making, production schedule. And the thing about these vector of production schedule, the production schedule tends to depend on each other. Okay, so A is what they call is a matrix. That's why it's capital, right? It's a matrix of, and it's the technology matrix. Why didn't I just say technology matrix? Technology matrix. D is what they call external demand. Whether you want to know what this actually thing is, you don't just need to recognize these the phrases, okay? First equation is these two most important things, but basically it tells you that the vector of production schedule equals A times X, which is the internal demand, plus D, which is the external demand. The difference between the two is that the internal demand is like one thing could depend on different amounts of the other things, so they're interrelated, and that's what A matrix tells us, how they're interrelated, whereas D is like outside the system. It doesn't depend on the interrelatedness of these x's. You can see that once we've written this down, we can get the second equation and then we can solve it, because that's just the inverse matrix. What you want to be sure of when you're writing this thing down, just to ensure that they're not going to dock you any marks, is write down on here by however many rows, how many columns A has. So if A is like 4 by 4, make sure you write I4 to show you it's that's the identity with 4 rows and 4 columns. What I want to show you here is how to construct this matrix A, the technology matrix, because in the questions they can give you like a load of stuff to read and you have to compose A before you can solve the second equation. We're going to construct this matrix A. I'll show you how it works using an example. Okay, here's an example. So a factory makes 3 products: big X, big Y, big Z. So it could be like, I think you've seen an example of like, coal, electricity, transport, something like that. And the production processes for each of these products are interrelated, right? So that means, like, yes, we have a technology matrix A. And then we've got the relationship, so we have to compose it. And so let's just write down this A. Technology matrix. The number of rows is going to be square. It's always square. The number of rows and the number of columns must match the number of products you have, so X, Y, and Z. And this is what I would do, guys. I would do, and I'm doing a different color just to show you. Oh God, what's going on here? It's say X. So I've written X, Y, Z around there, and that's not my bad handwriting. It's something. What is going on? So I would write the output there and the inputs here. And you can arrange it in any order you like. Since it's X and Y Z, it's just natural to go X, Y, Z, X, Y, Z. And the way you read it is like this. So this technology matrix A, we do this. It's all in currency units. The production for one unit of whatever. The production process for these products are interrelated. To produce $1 of X, that means we're looking down the first column because you're producing $1 of X, requires 0.05 units in dollars of X. So we write here 0.05. 0.1 of Y, so that's the input, right? On this row, we read second row. That's Y feeds in to give me $1 of X, and to do that I need 0.1 of it. Okay, 0.1. Sorry for the terrible pen, but I hope you're understanding what I'm saying here. 0.1, that's terrible. Okay, and 0.1 of Z to make $1 of X. 0.1 is what I'm trying to write right here. Alright. To produce $1 of Y, so that means now I'm looking down the Y column because that's what I'm producing, right? Because that's like out. Requires $0.4 worth of X. So I write X is going in and I want 0.4 of it. 0.4 of it. Okay. It's even worse than my handwriting on the board. Okay, and 0.4 of X, right, and 0.1 of Z. So 0.1 of Z. 0.1 of Z. Now I didn't say anything about Y, so we write nothing. Nothing has gone into it. And then finally, there just must be Z left we want to produce. So to produce $1 worth of Z requires 0.1 of X, so X goes in. And how much of it do we need? 0.1. Okay, and we need 0.2 of Y. 0.2 of Y. And it doesn't say anything about Z going to Z, so that's nothing. And that's my matrix A. It says also there are, each week there are looking for my pen, there it is. External demands of X, Y, Z of that. Alright, that's just, if I'm finishing this question off, that's X is equal, not just X, X, Y, Z is equal. Sorry, it's not that, is it? It's let little x, little y, little be the weekly production. So if we let X, big capital X, Y, Z to denote the products, little x, y, z denote the weekly levels of production. So it's little x, little y, little x, little y, and little z. We write is equal to this great big matrix A. So if let's suppose it's written there, times x. So this x, y, z again. Okay, so we'll write that down. X, y, z plus the external demand D. Alright, so it's got to be aligned in rows. So for demand of big X, we need 200. Okay, so we'll write 200. For Y, we need external demand coming outside the system's 500. 500, please. And they say don't work with kids or animals, nor should you work with technology. Look at this. Alright, and 1,500 units of a Z. Right, that's it. Once I write that down, we are done. And for the setup, and we're able to solve for Z once I rearrange it for the second equation I wrote. Okay, so that's it, folks. That's the notes, and good luck with the exam.